You've been lied to your entire life about what the universe looks like. Not maliciously, but just because the full picture is so staggering that nobody really knew how to tell you. For most of human history, we looked up and saw stars. Scattered, random, infinite, a sky full of glitter, beautiful, sure, but random, chaotic, no order, just stuff floating in the dark. That story fell apart the moment we started mapping it. In 1989, two astronomers named Margaret Geller and John Huchra were cataloging galaxies in 3D. Not just where they appeared in the sky, but how far away they actually were. What they found stopped the entire field cold. Galaxies weren't scattered at all. They were stacked together in a massive sheet over 500 million light-years long. It became known as the Great Wall, and it forced cosmologists to admit something uncomfortable. The universe had structure. Deep, organized, invisible structure, and we had completely missed it. That discovery cracked something open, because if there was one wall, there might be more. And if there were walls, what was on the other side? The answer is one of the most jaw-dropping things science has ever uncovered, and most people have never heard of it. It's called the cosmic web, and once you see it, you cannot unsee it. If this is the kind of content that makes you look at the universe differently, hit subscribe. There's a lot more where this is coming from. So what is the cosmic web? Think about soap foam, the kind you see when you wash dishes. You've got thin films of liquid stretched around enormous air pockets, and where those films intersect, the liquid bunches up into thick nodes. Now scale that up by a factor so large that the numbers stop meaning anything. That's essentially what the universe looks like at its largest scales. Galaxies don't float randomly through space. They trace along thin filaments, enormous threads of matter hundreds of millions of light-years long. Those threads connect at dense nodes where massive galaxy clusters sit. And between everything, vast, almost completely empty regions called voids. The Boötes Void is one of the most disorienting things in the known universe. It's roughly 330 million light-years wide. In a typical region that size, you'd expect thousands of galaxies. Boötes has a few dozen. It is, by almost any measure, close to nothing. Just an enormous bubble of near emptiness hanging in space. And it is not alone. These voids make up the majority of the universe's actual volume. Most of space, by sheer size, is essentially hollow. The filaments connecting everything aren't passive highways either. In 2025, astronomers reported observing a filament roughly 140 million light-years long whose galaxies weren't just grouped together. They were rotating together. Hundreds of galaxies spinning in coordinated motion along a single strand of the web. The scale of that is hard to process. We're talking about a structure so vast that the light crossing it would take longer to arrive than multicellular life has existed on Earth, and it's spinning. Now you might be asking, how does something like this even happen? How does the universe go from a hot, nearly uniform plasma right after the Big Bang to this intricate web-like architecture billions of years later? The answer starts impossibly small. In the earliest moments of the universe, quantum fluctuations, tiny, random variations in energy density, got stretched to cosmic scales during a period of rapid expansion called inflation. These weren't dramatic differences. We're talking about density variations of roughly 1 part in 100,000. Almost perfectly smooth, but not perfectly. And in a universe governed by gravity, almost does a lot of work. Regions with even slightly more mass pulled in more matter. That made them denser, which made them pull harder. Meanwhile, underdense regions kept losing material to their neighbors, growing emptier over billions of years. This runaway process, called gravitational instability, is what sculpted those quantum whispers into everything you see when you look at the night sky. The geometry isn't arbitrary either. Matter in an expanding universe doesn't just clump. It collapses in a specific sequence, first into flat sheets, then into elongated filaments, then into the dense nodes at their intersections. A mathematician named Zeldovich worked this out decades before we could see it directly. His approximation predicted a web-like outcome from basic physics alone, long before the surveys existed to confirm it. Baryon acoustic oscillations add another layer. Before the universe cooled enough for atoms to form, the hot plasma was filled with sound waves. pressure fluctuations moving at a substantial fraction of the speed of light. When the universe cooled and those waves froze, they left a characteristic imprint, a preferred scale of clustering roughly 500 million light-years across. That frozen sound wave signature is now woven into the cosmic web's geometry, and cosmologists use it as a measuring stick to track how the universe has expanded over time. But here's the part that should genuinely unsettle you. None of what we've talked about accounts for the majority of what's actually out there. The web we can see, the galaxies, the gas, the glowing filaments, makes up only about 15% of all matter in the universe. The rest is dark matter. Dark matter doesn't emit light. It doesn't absorb it. It doesn't interact with anything except through gravity. We cannot touch it, detect it directly, or produce it in a lab. And yet in every simulation we've built, from the Millennium simulation to the latest runs of Illustri's TNG, it's the dark matter that builds the web first. The dark matter collapses into filaments and nodes purely under its own gravity. And then normal matter, gas, stars, galaxies, falls into those pre-existing structures like water flowing into carved channels. If you could magically erase every star and galaxy in the universe, the dark matter web would remain almost completely unchanged. The galaxies aren't the structure. They're just the lights outlining a framework built from something invisible. The bullet cluster is the clearest evidence we have for this. It's two galaxy clusters that collided and passed through each other. The hot gas from each cluster, visible in X-ray light, got dragged and slowed by the collision. But gravitational lensing maps show that the majority of the mass from each cluster kept moving, passing through the other as if the collision barely registered. Dark matter and visible matter separated in real time. You can see it in the data. The invisible architecture and the visible lights don't always live at the same address. What this means for us, sitting here in one small galaxy, in one modest filament, inside something called the Laniakea supercluster, is genuinely strange to consider. Our galaxy's position in the web wasn't chosen. It was inherited, set in motion by density fluctuations that existed before the Earth formed, before the sun ignited, before any of the atoms in your body had been forged inside a star. Galaxies in dense cluster environments look different from galaxies in voids. They're more likely to be elliptical, red, and no longer forming stars, quenched by the chaos of constant gravitational encounters and stripping. Void galaxies tend to be blue, gas-rich, still actively building themselves. The web doesn't just describe where galaxies are, it determines what they become, which raises an unsettling question that cosmologists don't often linger on. Two civilizations, one in the core of a massive cluster, and one in a quiet void, would look out at radically different universes. Different numbers of neighboring galaxies, different merger histories, different rates of stellar violence, different raw materials for planet formation, the same physical laws, but wildly different cosmic neighborhoods. Their science, and maybe even their conception of what the universe is, might diverge in ways we can barely model. We can simulate the web with extraordinary accuracy. We can map it across billions of light years. We can identify filaments, classify voids, and predict how structures will evolve. But the two things that actually build and control all of it, dark matter and dark energy, remain fundamentally unexplained. We know what they do. We have no confirmed idea what they are. Decades of direct detection experiments have turned up nothing. The architecture is visible, the materials are not. And the web is still changing. Voids expand, filaments grow denser, nodes consume their surroundings. Whether that process continues indefinitely or eventually freezes depends on how dark energy behaves over cosmic time. And current surveys like DESI are racing to find out. If dark energy evolves, the future of the cosmic web looks very different from anything we've modeled. The entire large-scale story of the universe might need to be rewritten. There's a number that doesn't get cited enough. The cosmic web emerged from density variations of 1 part in 100,000. That's the seed. 100,000 parts the same, 1 part different. From that almost nothing difference over 13 billion years, you get filaments spanning billions of light years, rotating structures 140 million light years long, and at least one pale blue dot in a quiet filament where something evolved that could sit down and try to understand all of it. The universe may not be designed, but it is deeply structured, and we are stitched into that structure at every scale, whether we notice it or not. And that realization quietly breaks one of the most comforting assumptions we carry about reality. We tend to think of ourselves as observers looking out at the universe from a neutral vantage point, as if we're standing outside the system, objectively measuring it. But the cosmic web makes that impossible. We are not outside the structure. We are embedded inside it. Every measurement we take, every theory we build, every cosmic question we ask is filtered through the specific filament we happen to occupy. Even our most basic observations, how fast galaxies recede, how often stars explode nearby, how much radiation bathes interstellar space, depend on where we are in the web. Cosmology assumes the universe looks roughly the same everywhere when averaged over large enough scales. And mathematically, that's true. But experientially, it isn't. Local geometry matters. Environment matters. And that means our picture of the universe is unavoidably provincial. There's also a deeper implication that rarely gets discussed outside specialist circles. The cosmic web doesn't just organize matter in space, it organizes time. Galaxies in dense nodes age faster. Star formation shuts down earlier. Heavy elements are produced sooner. Entire regions of the universe chemically mature at different rates. In that sense, the universe doesn't have a single present. It has neighborhoods living in slightly different cosmic eras.